All right. First, a couple comments on the assignment. There's a few things. There's a couple obvious things that I'm going to say. The first one is all those things on your desktop, right? That you program. I've seen some pads of paper. I've seen some lamps. What happens if I said, "Oh, gee, why don't you move those over here?" Could you do that easily?
Yeah.
All right, without changing all those little coordinates you've hand-coded into the code, all right? Could you have done that easily?
Yeah.
The answer is pretty much yeah. Now, the objective of that statement is that graphics sets up perfectly for C++. Okay, that everything on those tables should be a separate class in C++ and should have a draw function associated with them. Okay? Then they should have a draw function, right, associated with them. Every single thing sets up as a class just beautifully in this field. It has a draw function associated with it. It could also have a transform function associated with it, which you gave it a matrix, right? Built up from the C++ classes that maybe I give you or something else, but you could give it a 4x4 matrix and say transform. And then in the draw function, what it would do is take your hand-coded coordinates in there for a very generic piece of paper, and it would transform them all before it called GL vertex, right? Or it would set up a model matrix. Go look it up, right? Because we've done that. Set up a model matrix before you actually called them. There's a push matrix and a pop matrix command, so you can push your matrices on the stack, add another matrix to it. These are all model matrix commands, okay? You can push a matrix, add another matrix to be done using GL translate, GL rotate, all these commands, and then you can pop, when you're done with your draw routine, you pop the matrix stack again using pop matrix. And in this way, you can set these things up so that you can move them around, you can do all kinds of things with them. And so a desk, right? When I code it up, I have a desk class, I have a lamp class, I have a piece of papers class. It's even sometimes even more than this. The lamp has a light bulb class. It has a light switch class in case I want to push the light switch down or something, show it moving up and down. It has all these things, and I build a draw function into each one of these things. Right? And I draw them very generically, and then I can move them around using the transform and the model matrix command. So this is one of the objectives in this class, is to get you to think in much more of a C++ framework for all these things that we do. Okay? We all have, everybody who writes in this field, we all have a camera class. We all have light source classes, which I'm going to do today. Right? We all have these various classes for the things we build. Okay? And then we construct them up, and they all have a draw function in them. Right? The common thing between all these classes has a draw function. I might make up a room which contains a desk, which contains pads of paper, which is a class called room. It's got a draw function. Draw function says draw a desk, draw pads of paper, draw this, draw that. Right? That's all it says. Okay? And then my paint GL command, right, in my canvas class or whatever, all it says is draw. Room draw. Or something like that. Okay, so this thing sets up so nicely for C++, and when you do this, you can add things, you can move them around, you can modify them really easily, and so basically you should think in your head, right, that all these things, don't do just straight line code through here, right? That's hard to manage. Set up everything as a C++ class. It works really, really well to do things this way. And since all these classes look almost identical, right? I've always preached with C++, you get one generic .h file and one generic .cpp file, right? And then what I do is once I learned C++ for the first time, I learned the global replace commands of the editor that I like to use. I'm a VI guy, right? I learned the global replace commands. So I put in a vector class and I globally replace the word vector with lamp. And I have a lamp class that's almost done already. Right? And I go into the .cpp and I replace all the word vector with lamp, right? And I go in and I change the few commands that need to be changed, okay? And so I can create these classes really, really quickly from one thing to another. So it's something that you should think about. This thing sets up really beautifully for object-oriented languages. And graphics sets up really beautifully for it because all the things we have out there in our scene are objects, right? And they all set up very, very nicely for them to have a class, etc. So you'll see a lot of us, you can almost figure out what we're doing by looking at the names of our classes that we have when we get done. So that's one thing. And the other thing is that first question on the assignment, which said, show me what something looks like in image space. Okay? Well, to get it into image space, right, you have to have right? You have to have a camera transform followed by a viewing, or a camera matrix followed by a viewing matrix, of which you're going to take all the points of the objects that you want, x, y, z, and 1, right? These are all the points of your cylinder. And to get it into image space, you're going to have to hit it by these two matrices, a camera, and get out something x, y, z, and w. You're going to have to right? And this is now in image space. Okay? But you need to set up these two things. And if you remember, this one has alpha and near and far in it, right? And this one has a whole bunch of rotates and everything to get you down to the, so that you're looking out on the z-axis, on the negative z-axis. So this is an image space, and so what you want to do is you don't want to set up look at and perspective to view those points. You want to look at and perspective to view these points. Okay? And then what you want to do is see, the whole objective here is to make you construct these matrices and understand them. Okay? You have to construct these two matrices yourself. Okay? Those guys you have to construct yourself. And so then over here with these points, after you get done constructing those things, doing the matrix multiplication, dividing by W and everything, now you have points that are in image space, and now you can view this using GLU perspective and GLU look at, right? Where maybe you're looking at this at 0, 0, 0 in image space, okay, as the center of attention that you're looking at. So, right, if you want to look at this somewhat naively, there's one C and V here to get things into image space, and then there's another C and V over here in image space that you're going to construct to do it. These can be constructed with GLU perspective and look at. Those you need to construct yourself. Okay? All right, the whole objective was to get you to look a little closer at those matrices and understand what's going on. Okay? I've got some nods this time. Okay. All right, so today we're going to move off the mark. I'm going to, you see, you can probably see what's coming here. Ken has you doing a really generic camera slider thing to modify all these parameters. We're going to do it a lot easier here. Right? We're eventually going to have an airplane that we fly around our things, okay, and look at them. Okay, we're going to fly an airplane around. It's actually really easy to do. You can couple it to a mouse, okay, and kind of move the mouse around and tilt it from back and forth and have it flying. Or if you move the mouse back, it'll go up or down. Or if you play with the wheel or something else, it'll increase in speed or decrease in speed. I mean, it's actually pretty simple to do. There's also one called a trackball, which I'm going to do next time. I'm going to do something called quaternions next time, which are kind of interesting, and they come out really nicely. But today what I'm going to do is I'm going to talk about color and shading. And if you look at the graphics world these days, most people don't talk anymore about how do we view things, et cetera, et cetera. Those problems are almost solved in this world. What they talk about is, what do things actually look like? How do they reflect light? How do we get them to look the way we want them to look? And this has all to do with color and shading, okay? So, and what I'm going to say here is that this stuff is really hard, okay? This is physics. It's the physics of light energy bouncing off some surface and how much of that energy gets back to your eye. Okay, and this is not trivial to do because these surfaces, kind of light energy goes into them and actually doesn't really, all of it doesn't really reflect off. These surfaces have little tiny, we think of them as having these little microfacets running around. They reflect light in different ways. Okay, some of them are very dull surfaces and they reflect light in kind of all directions. Some of them are really shiny surfaces. Those microfacets are kind of all oriented a little bit. Okay, and they reflect light almost really nicely, perfectly reflecting it. Some of them are mirrored surfaces and they do reflect light, as you would think they do. Some of them are dielectric or metallic surfaces, and they're the ones that you just throw up your hands with, because in that case the energy comes in, runs along the surface for a while, okay, until the surface says, I've had enough of this, and then reflects off in some direction. Okay, and this running along the surface, there's just no way you can model this. Okay, we just kind of don't even think about those things. You know, so this is a tough problem. Color is also a tough problem. Okay, and in the graphics world, we have simplified color down into basically a simple little system that looks like this. We have this 3-axis system called Rgb. Okay, called Rgb. It's a simple little 3-axis system that we use. Now, it's not, there are colors you can't get in this system, believe it or not. Really what color is you take light energy coming off, you look at the different wavelengths of light energy, you integrate them over a particular color function, and these are the colors you get out. We can't do this integration, okay, this integration step. Actually, we can, but it takes a long time, and typically we don't, okay? So we simplify this down to what's called an Rgb system, okay? And in here there's a cube. Use your imagination, that's a cube. In here there's a cube, okay, where we think of this as these Rgb values as lying between 0 and 1. Here. And inside the cube are numbers between 0 and 1. So out here, for example, is the point 1, 0, 0. And this is red. Okay? This is red. Up here at 0, 1, 0 is green. The color green. Out here at 0, 0, 1 is blue. Okay? And typically when you look at a typical graphics processor, you get one byte, right? Values 0 to 255, 1 byte for red, 1 byte for green, 1 byte for blue, right? Rgb, you get these 24 bits of color, right? Which gives you 2 to the 24th colors, which isn't bad, okay? Which isn't bad. You get 16,000 yellows if you want for your banana, okay? So it's not bad to do. And what we have to do is eventually figure out how to manipulate these colors into the things we want things to look like. Now it's hard to choose things in here. So you have red, green, and blue. This point out here, halfway between red and green, is yellow. Turns out. This one out here, halfway between green and blue, is cyan. This one out here, halfway between blue and green, is called magenta. It's called magenta. This one down here at 0, 0, 0 is black. This one up here at 1, 1, 1 is white. Okay. And anything on this dotted line between black and white, these are the grays. Okay. Those are the grays. And along that diagonal, where all of the coordinates are the same, right? Red, green, and blue are all the same. Those are grays along that diagonal. And this is the color space that we typically work in, the Rgb color space. You'll see that if you want to specify color in OpenGL, the color command, right, GL color takes R, G, and B, right, as various things. Usually they can take either number 0 to 1 or it can take 0 to 255, whatever.
In OpenGL, like we set color with from 0 to 1.
Right.
But for example, I accidentally entered, instead of like 200.2 something, I entered like 200 something.
Right.
And it still worked.
Sure.
But it just made everything blue because it was blue. So how does that
What
work?
happens is it clamps the number, right? So if you set a number bigger than 1, it'll make it 1. If you set a number less than 0, it'll make it 0.
When it makes it 1, does it create the other two numbers you have in there to be the ratio, or does it keep the number?
Nope. It will just clamp. There are different ways of clamping, and I'll bet you that OpenGL allows you to do any of these if you look inside deep enough, right? But in general, you can think of it as just clamping. If you tell it green 200, it'll make green 1, okay? And keep right on. And going. So there's no varying the others, right, to make it work out. Okay, the problem with this system that everybody has is, suppose I want to make Dodger blue, something we were playing last night, or suppose I want to make sandish, a color that looks like sand, or suppose I want to make orange, right, or something like. How do I do that? And it's not obvious how you would take this thing and do it. Okay, how do I get a certain color that I want? Okay, now there are color choosers out there, and probably many of you have seen them, and but it's not quite obvious in this RGB system how you might manage these colors. And so there have been other systems invented here to do so. One thing about this RGB system that is a little harder to understand is that it's an additive system in the case that I can kind of add colors together and get them. But if I add, it's not quite clear. If I take crayons out, right, and I take a red crayon and I smush a green crayon over the top, I don't get yellow. Okay? This is a slightly different system than what you get with crayons and other things. Okay? There's also a system called CMY, cyan, magenta, yellow, out there, right, which is kind of the opposite of this. Okay? It's kind of the opposite of this. And it's used mostly in the film industry. Anybody who uses Photoshop knows that there's a CMY alternative to an RGB alternative. Okay. One of the models here that people quite frequently use to choose color is called HLS, which stands for hue, lightness, and saturation. Some people call this HLV, where the V is called value. V is the same as saturation in this case. And this one is developed as a cone, okay? And what it is it's as if you looked at this cube down this axis here. This thing would be on top, and around the outside would be the colors. Red, yellow, whatever, around the outside would be the colors around the outside. And then you would go from white to black kind of down the axis. And what they've done is they've translated this, and there's actually code out there in my C++ classes, if you like, that takes this and translates it into a cone like this. Okay? Where around this cone here, now if you think of this looking kind of down this axis, around the cone I have red, yellow, green, cyan, right around the cone here. So here might be red, right? This is green and blue, and there'd be magenta, etc. around this cone. And then there's a line going through here. It's actually a straight line going through here, okay, of which this is white and this is black. And so the hue here is around a circle, goes from 0 to 360 around a circle. Black to white is the lightness, that's the L value, right, which goes 0 to 1. So, and then the saturation is the gray values are on this axis, and the saturation is how far I get away from this axis. So as the saturation value goes less, right, what happens is your color washes out to gray. Okay? You take your color, it'll wash out to a gray level as you go in. And a lot of people will like to do this to define their colors. It's a little bit easier. And if you go into the color choosers that you can get on any machine here. You can either deal in RGB space, select colors in RGB, or quite frequently you can select colors in HLS. Right? And a lot of people, including me, find this a lot easier to visualize. Let's see, if I'm going to get a sandy color, it's going to be kind of a yellowish red, and then I'm going to wash it out toward gray. Right? And I'm going to get a sandish color. And a lot of us can pick our colors a lot quicker in this system than we can in that one. Okay? This is the one we calculate with, though. Okay? Everything calculates in this system. Right. And it takes a little while to get used to these guys. It doesn't take too long to get used to these guys. But, you know, red plus green equal yellow. I mean, you know, if you've worked with crayons as a kid, you know, doesn't quite make sense, but it does in an additive formation. Okay? So these are the color models. And they take a little while to get used to. But what you're going to have to do is you're going to have to specify, for each of your objects, you want to be able to specify RGB colors. Okay? So quite frequently, all of our objects contain not only XYZ coordinates, they also contain a color. Okay? And they're going to contain a lot more than a color. They're going to contain some material values too, so that we can tell how light reflects off these objects. Okay? That's one of the things we have to have. All right, so here we go, light sources. Okay, now I have to show you how hard this is. Let's take these light sources up here, okay? And if you look how light reflects off these things, right, that you get a couple things. You've got light energy coming out of these things, okay? And it's reflecting, say, off the table in front of you, this light energy. Okay, and it kind of reflects in all directions, primarily maybe in one direction, but kind of reflects, diffuses and kind of reflects in all directions. And so if you follow a vector from this light source down to your table, right, once it hits the table, right, you got a certain amount of light energy hitting the table, right, it's going to scatter light in all directions. So there's a vector going out toward that back wall maybe, and a certain amount of that energy is going out to the back wall, right? And that back wall, it reflects light again. There's a certain amount of energy coming back here to the blackboard, right? A certain amount of energy coming here. And then the blackboard reflects light again, and maybe there's some certain amount of energy going back out to the back wall again, okay? And then finally, this reflecting a bunch of light, and it's coming into my eye, and that's what I see, okay? And you can see that you've got light reflecting all over the place. In fact, reflecting almost recursively, because the back wall can be considered, all the light that's reflecting off it can be considered as a light source for the blackboard. And the blackboard, alternatively, can be considered as a light source for the back wall. And you've got recursion going on. And people realized almost immediately that there's no way we're going to do this, okay? There's absolutely no way. And it turns out, well, we did do it anyway, okay? We did do it anyway. It takes a long time to do, but we can do this. We can actually take a closed environment like this and calculate a steady state light solution inside this closed environment. Turn the lights off and get only the light coming in the windows, and we can calculate it again. It takes a while to do, 10 or 15 minutes sometimes, right? But we can do that, okay? And I mean, we just borrowed something called radiative heat transfer from the mechanical engineers, okay, and figured out how to use the radiative heat transfer algorithms to do light energy rather than heat energy. It was actually pretty interesting. But in general, that's too tough to do. And in OpenGL, everybody said, no, no way, okay? So what we had to do was we had to figure out how are we going to figure out how light reflects off surfaces and do so simply. Okay, and these models were made at the University of Utah in about 1976 or 77. Okay, and a little bit of it makes sense. Okay, the real crux of this is probably one of the most famous hacks that's ever been made to physics in the history of the discipline. Okay, but it actually kind of works, and so we use it. So that's what I'm going to show you today, is this hack as we go along. Okay, so what we got is this light energy coming off here. What I'd like you to do is I'd notice that this table is kind of reflecting light all around, okay, in different ways, different than the chairs reflect light, etc. Okay, the color has to do with how much is absorbed by the energy, how much energy is absorbed and how much is reflected. Okay, and you know, this is reflecting only the blue light, say, the blue light energy coming from the chairs, not the red or the green. You can think of it that way. And so we've got to specify for our things how it reflects this light. And we usually do so with each one of the R, G, and B components. Okay? Now, if you think about it, that's not very good because there's a continuous spectrum of light energy coming from these bulbs. And we actually know a lot about that light energy. We actually have the spectrum of energy for fluorescent bulbs and all. There's a continuous spectrum of light energy, coming from these bulbs. And we're going to say, okay, we're going to sample just red, green, and blue. Right? So we're going to do it with 3 of this, it's like taking a complete continuous curve and say, okay, I'm going to sample it here, here, and here, and that's good enough. Okay, I can tell everything about the curve by sampling it. Of course you can't. Okay? But this is what we're going to do. We're going to do it just for red, green, and blue. And then we're going to start making some assumptions, okay? Now there's a couple things. Number one, let's see, I need to get you to think about going into your closet at night. And this is a beach ball, okay? You've got this colored beach ball, okay? And you've got a flashlight over here, right, that you're going to shine on your beach ball, okay? And your beach ball is going to reflect, you're in a dark closet shining this flashlight on your beach ball. And this is the way we model most things now. Now the beach ball is going to reflect this light, right, around a little bit. And it's going to bounce off the walls of the closet and everything else. And so the backside is going to be a little bit illuminated and all, right? But as you're standing out here, you're going to see a bright spot kind of on the beach ball, right? Which is where the light really directly shines on it, okay? And it's going to be brighter on one side than another side, etc. Okay, we have to model all that, how it's done. Now, if you think about this, if you look at the surfaces here, they kind of look the same, but if you look at the floor, I think most of you can see that. Can you see the reflection of the lights in the floor? Okay. And the interesting thing about the lights, the table kind of looks the same no matter what I do, but these lights on the floor, if I move, they move. Okay? So the lights on the floor depend on where I am, right? And that's going to be tough news for us here, right? Because they move where all I'm going to have to do is I'm going to have to remember where the camera is, right? And I have to remember where the light is, okay? Now these guys are tough. We can't assume that we have these nice continuous cylindrical light strips, you know. We're going to assume we have point lights in our world. Okay, so the lights are kind of like cameras here. We use a point-based camera, right, a pinhole camera. We're going to use kind of a pinhole light source too. So first thing to recognize here is that light sources are point. Okay? And the light has a color. It has a color. We can do colored lights, right? Mostly we're going to think of our lights as white, but lights do have a color. Okay? And so I'm going to model 3 things. When you think of the flashlight in the closet, you got the flashlight, you're holding it kind of close to the, to the beach ball. Light's bouncing off the beach ball, then it's bouncing off all the walls, and it's, kind of illuminating the closet, right? And all this background light, we're just going to assume is a constant. Just one single value, okay? And I told you, this is really simplistic compared to what really goes on, okay? So all background light is which is called the ambient light. Here is a constant. Okay? And this is actually kind of misnamed. I don't mean the actual light itself as a constant. I mean the energy that this reflects. You'll see is going to be a constant. So all the background light I'm going to lump into these ambient light constants. Okay? That's number one. Number two, when you look at a surface and you put light into a surface, it scatters light. You can think of it as having little tiny microfacets on the surface that reflects light. That's the way we like to think about it. And it scatters light out. Well, In physics, we know that a perfectly diffuse surface scatters light in a very particular form. This is one that kind of scatters light equally in all directions. Okay? And when it does, we're going to look at something called Lambert's law. Right, which says that if you light is scattered off a perfectly diffusing surface by some constant times the cosine of the angle, where I'm going to have to draw a picture like this. Here's our surface. Here's a normal vector to the surface at some point. And if I have light coming in from this light source over here, here's the light source. If I have light source coming in, here's the cosine of the angle, okay, it's going to scatter light away from the surface, right, depending on the cosine of this angle. And if you think about it, that kind of makes sense. If I'm really at a big angle from the surface, right, I'm barely grazing it, it's going to scatter, and if it scatters things, it can't scatter very much of that light, okay? It's going to scatter very little of that light. And in that case, the cosine of near 90 degrees is 0, almost 0. Okay? Whereas if it's directly above and looking straight down at it, I'm going to scatter a lot in that area. Okay? That's where I'm going to scatter the maximum amount, and that's where the cosine is 1. So it's some constant here, right, called the diffuse constant. Right, in order to scatter light in that way. So these two things I can put together pretty easily, okay? Now, by the way, this is where light is scattered. Lambert's law says scattered away from a perfectly diffusing surface. As far as we know, there is none of those, but we'll assume that that's the case too. Okay? We'll assume that that's the case too. So the way we put these things together is to do something like this. We're going to call this illumination here, and that's going to be equal to, let's see, how do I get color out of something? I'm going to have this picture again. Here's this with a normal vector and a light source out here. Oh, light source. Light sources are stars. And here's my theta here. Okay? Now, if that's n, and this is a vector, if I have a unit vector n and a unit vector L out here, we notice that n dotted with L, these two vectors, happens to be the cosine of the angle between them. It really happens to be the length of n times the length of L times the cosine of theta. If these guys are both unit vectors, the length is both 1, and I get the cosine of theta. So I can actually calculate the cosine of theta just by taking this dot product. Dot products again, right? This world is all dot products. Okay? So what I'm going to do is I'm going to calculate the illumination that comes across here, the color. I'm going to have 3 different equations because I'm going to do one for red, green, and blue here. And it's going to look something like this. Okay, now there's a C here, which is let's see, let's call it, what should I call this? How about a C, right? C red, C green, and C blue. These are the base colors of the object, okay? Where can I put these? This is the base color of the object. So if you want an object that's red, okay, you would put 1, 0, 0 in here. If you want your beach ball to be red or your cube to be red or whatever, you would put 1, 0, 0 in here. Okay? And then we would multiply this times the amount of light that's coming in. So there's the ambient red. These are the ambient constants. Right, there's a red, green, and blue. This is how much how much is reflected back from the ambient. So ambient is always a constant here. These are normally like 0.2. These constants are about 0.2. Right, so we assume there's a little bit of background light. If we make it 0, if we have no ambient light, then, for example, the back sides of our beach ball would be black, right, and not able to be seen, which is not good. Right? And then we're going to do plus the diffuse red times N dotted with L. Okay, and we do it this way. Now, notice, I mean, this is the type of equation you would probably write down. Okay, and this is almost it, turns out, that we do. So we assume things are perfectly diffuse reflectors. Now, notice that we have, we used to have to store RGB for each one of our, just a red, green, blue color for each one of our objects. Now we have to store things that say what the background colors are. That's quite frequently almost fixed for the whole scene. But all of our objects reflect light differently, right? The blue chairs reflect light differently. And so we've got to specify now for our objects some diffuse constants. Okay? And this is it. Well, there's one more term out here, and this is the one that caused everybody trouble. Okay? This is the one that caused everybody trouble. And it comes from these lights that are up here. And if you notice that the reflection on the floor is the color of the light, right? If these were red lights up here, that reflection would probably be red colored on the floor here. And so what we have to do is the following. Is that if we have a surface here, here's the normal vector to the surface. By the way, this looks kind of, you might ask, how do you calculate normal to a surface? Right? All of the surfaces we deal with will have normals that are easy to calculate. Polygons all lie in a plane, so they all have a nice normal, which is perpendicular to the polygon. You can take the vector that connects the first and second point and second and the third point, take their cross product, you get something perpendicular. And it's actually pretty easy to do. In fact, the system will do that for you in general. Okay? You have a light source out here, okay, going out, and you have another vector called L. Okay? And then you have a vector called V out this way. And here's my eye pointer camera out here. And you have a vector out here. Like that. Okay? Now, if I had only point lights up here on the lights, the reason that I have to include V now is because these bright spots move around with me, right? It depends on where I am. Lots of times this diffuse reflection off the table doesn't depend on where I am in particular, right? It's just this color happens anyway. But what I have to do now is I have to figure out how this light reflects off something, okay? And this caused people a lot of problems, for a lot of years actually. It caused people a lot of problems how to do it, because in general you assume that the light reflects, you know that if this is theta, you draw another vector over here which is theta, and you know that the light primarily reflects out that way, okay? Okay? But you know that all the incoming light is kind of spread, right? It's kind of spread, and some of it, most of it reflects out that way, but some of it is not quite reflected out that way. And this is what they had a real hard time doing, is figuring out how this light actually reflects. And this model is called Phong shading, after a graduate student at University of Utah. And he threw in the very first thing that he thought made it look right. Okay? And it turns out that this thing has stuck around. And what he did was he said, let's measure the angle. If this thing tapers off here, okay, let's measure this angle, phi, right, which is the angle between the point back to the viewer and this perfectly reflecting direction, okay, for the light. Let's measure that angle. And if I'm off a bit, right, if I'm on the perfectly reflecting direction when phi is 0, then I should get almost all the lights reflected back to me. And if I'm off it, right, what will happen is I get lesser of the light reflected back at me. And so what he did was he said, let's look at this. It's called specular light. Okay, and he said, this is easy. What I'm going to do is I have this perfectly reflecting vector here, and I'm going to measure it against this other vector v, and I'm going to kind of do a reflecting vector. How about calling this guy r for a second? Okay, I'm not going to use it, by the way, but what I want to do is I want to calculate v dotted with r. Right, because that gives me a cosine effect, right? As I get farther away, as phi gets bigger, this gets smaller, okay? You know. And this is what he did, and it's what we don't do, okay? And the reason is that it falls off too slowly, right? What you want is a highlight on your objects to make it look realistic. These things on the floor are highlights. They don't diffuse a lot. They actually reflect back at me, and then afterwards they kind of fade out really quickly. And so what he did was say, well, this isn't good. I'm not going to use this one. By the way, it's going to take me some iterations to get to the right one here. Okay? He said, this isn't any good, but what I'm going to do is I'm going to say this one, what I'm going to do is raise this to a power. Now, if you think about that for a second, here's cosine, right? And this is 1 up here, right? And here's cosine squared. And if that's 1, well, you know at 0 this is 1. 1 squared is 1. That's okay, right? 0 squared 0, that's okay, right? But what happens in between here? Well, if you take a half and you square it, you get a quarter, right? So it goes down, okay? And it does something that looks maybe like this, right? Start dropping down, okay? What he said, well, that's not good enough either. Let's do that one. Let's do this one, okay? And what happens is it starts looking like this, right? Because a half squared is, right, a half to the 4th power is a 16th. Right, it goes down really fast. Okay, but this one always stays at 1. And what this type of a function does is if you go off of 0, right, if the angle is off of 0, this thing is 1 at 0. You get the maximum out at 0, but if you go off of it, it dies off really quick. Okay? Now, you show this to a physicist, they'll go crazy. Absolutely crazy, because this is not the way the world works at all. Okay? It is not even close to the way the world works at all. Okay? But it was the one that he did. Okay? And his thesis, his PhD thesis that developed this and all says, wow, cool, if you make this number bigger up here, okay, then you get, so if you make it 100, you get things that look really shiny, and if you make it 5, you get things that look really dull. Okay? And this was the result of his thesis. And that number is bigger is shiny, less it's dull. And this number up here, this n, is called the glossiness. It's called the glossiness factor. So I'm adding another thing that we got to tell you about about each surface, right? Each surface has got a glossiness factor. Okay? And what that glossiness factor does is it just makes things die out quickly, right? So it makes things look, if the glossiness factor is very high, they die out very quickly, and they look like around this reflecting direction, it looks really shiny. Okay? Otherwise, it'll diffuse it way out, and it'll look dull. Well, turns out this wasn't very good either, because you got to calculate this this r vector, and it turns out that was hard. It's a little harder to do. They didn't like that so well. And it turned out also in early computers, raising something to the 100th power is expensive. Okay? And so they had all kinds of hacks to raise this around. But it turns out that there's another way of doing it that's actually pretty easy to calculate. and that's this one. If you have this vector n, this vector L, up to a light source, this vector V, out here, out to an I point, like this. If you have this vector, then there's another vector here that we commonly today call H. Okay? And it's the one that's exactly halfway between L and V. Okay? Exactly halfway between L and V. That one's easy to calculate. You do L plus V and divide by the length. Okay? That one's easy to calculate. Okay? So here's this vector H, and then what we do is we measure this angle. Right? Because if this angle were 0, then our V vector would be at the perfectly reflecting direction, right? So this H is kind of the normal. If the normal were H, right, then it would be reflecting perfectly. And then we measure how far H is off the real normal here. And so, you know, this is the way things are done. So really what we take here is n dotted with h to the m power, to the, I've got n over there, right? Too many n's running around. And times some constant in front, which is the amount of the, it never reflects all the light back to us, only a portion. Okay? You following me? This is kind of weird. Okay? So now what happens is what we do over here, and I'm going to go back to this board, is we add on this specular thing. So this is see the light. We have to, oops. I'm going to, let's call, see, this is the color of the light source, red, color of the light source, green, color of the light source, blue, because this component is times that, times a specular constant, red, S green, S blue, times n dotted with h to the m power, like that. And here's our color model that we use. So it includes the base color, and then how much light reflects off that, how much of that base color is reflected, right in here. It's got a constant amount of background light, and then we assume it's a perfectly diffusing reflector, which it's not, but we assume this anyway. Okay? And we get this, and we put in these diffuse constants, and then we say how it reflects light specularly, these highlights in light off the floor, right? And we have to color this by the color of the light source, right? Which quite frequently is 1, 1, 1 here. Light source is white. And quite frequently this is 1, 1, 1. But it doesn't reflect all the light back, so that we have to make these things come out. And we get a number out which is RGB, right? Between 0 and 1. And that's how, this is how we color our objects. And so if you notice the things you have to provide here, there's these ambient constants, which are kind of the amount of background light that's scattered off this object. Kind of, you can define that for the entire object, maybe, not for just a particular little piece of the object. We have to put the base color in of the object. We have to put the diffuse, how it reflects light diffusely. Okay, this is normally in the ambience normally in the 0.2 range, the diffuse in the 0.5 to 0.6 range. And these guys in the 0.2 to 3 range. We have to also specify these guys. And we also have to specify these guys. And then we have to specify the color of the light source we're talking about here. So all of a sudden we went from specifying a color for our objects to we have to specify the ambient, the diffuse, the specular, the color of the light source, and this glossiness constant. So there's about 10, right? If you think of light source stays kind of fixed, ambient kind of stays fixed, right, for an object. Then there's 3, 6, 9, 10 objects we have to specify for each thing we have, okay, for color. And there are routines in OpenGL to specify ambient, diffuse, specular. They each have 3 components to them, okay. There are routines in OpenGL to do this. I'll show them to you next time because I'm out of time here. But there are routines to do this, but this is what we calculate. So we kind of have to sit down and figure out what all these colors are. Okay? Now it's going to get more complicated because even though this equation is incorrect, and oh, by the way, we here at UC Davis published some papers back in the early 80s where we actually did the real calculations, okay? And we integrated over the amount of energy coming over. We did these things. Took forever to do. And what we find out basically is that these guys are really pretty good as long as your surface looks like plastics. Okay? These actually do a pretty good job, which is why all those kids in Toy Story look like plastic kids, okay? And why all those people on the spacecraft in WALL-E look like plastic people, right? These are the models we use. They make things look like plastic, okay? But you know, it's not too hard. You have to get used to thinking of all these things, and you have to put in all these parameters for every object. Now, most of them, we boilerplate them in. But we're going to start playing with this equation, right? Suppose I had, quickly before I end, suppose I had an orange ball, and I wanted to make it into an orange, the fruit. Okay? Well, an orange ball is just smooth orange, right? I can stick orange over there, and I can define specular and diffuse constants. But what if I want an orange for the fruit? What I do is I start playing with the normal vectors to the surface. Because in an orange, the normal vectors vary, right, over the surface. So suppose I let the normal vectors kind of vary randomly. And I smooth things over a bit. Voila, I get an orange out. And so what people have done here in the shading world is we are going to play with every single one of these things, okay? We're going to play with these guys out in front. That's called texturing, okay? We're going to play with the color that you map onto the surfaces, okay? And there's going to be other parameters for that. We're going to play with N. That's called bump mapping, okay? We're going to play with L. That's playing with the light source and where it comes from, and we can vary reflections on things. And we're going to play with the specular stuff, okay? We can even play with the glossiness number. One guy wrote his girlfriend's name in glossy letters, and he pan over the surface with a light source, and you can see, you can see the girlfriend's name by how it reflects light, okay? We can play with anything in this equation, and this is called shading. There's things called shading languages. There's things called RenderMan. All these things come from playing with this single, simple, god-awful, not even accurate equation, okay? That comes from, and this is probably the biggest hack, one of the biggest hacks in the history of computer science, okay? To throw that thing on there. Doesn't even correspond to reality at all, but it makes things look okay. All right? It's all right. I'm done. I ran a little bit over. I apologize, and we'll see you next time.